Welcome everyone. I hope it's all going well this weekend. Feel free to say hi if you're here already. I hope everyone's keeping well and you're having a good weekend. Yeah, hopefully we're all good. It'd be great to hear from you in the chat. If you're here, we've got a big topic planned today. We're looking at log rules, logarithms, which is very much a kind of new idea at A level for most people. So do feel free to say hi if you're here and you're ready to start. It would be great to hear answers and questions in the chat as we go, if you guys want to clarify anything or check over it. So do say hi and welcome if you're just joining. So as I said, we're going to be looking at log rules today and logarithms. So I'm going to just get ready to share the screen. But yeah, welcome if you've just joined. And we'll get started shortly. It'd be good to hear from you in the chat. So log rules, logarithms is very much an A-level maths topic. And we're going to be going from basics and building it up. So logarithms and log rules is kind of normally a year 12 topic, but we'll also be looking at it as a topic that grows into the kind of year 13 pure maths as well. So welcome. Do feel free to say hi. It'd be lovely to hear from people. And we're about to start shortly. So logarithms is what we're looking at. And kind of, I'll talk a little bit about snap revise at the end and the web class structure in general. So hopefully this will give you a good idea of how we'll progress through the logarithms topic. But welcome. I hope you're all having a good weekend and keeping well. It's been probably a full-on term for a lot of you, especially those studying towards A levels and year 12 and 13. This is quite a full-on time. But yeah, I'm keeping an eye on the chat. And as I said, do feel free to say hi and we'll get started shortly. That'd be great. Cool. Excellent. So here we go. I'm just about to share the screen. Welcome if you're just joining. We're looking at logarithms today. So let's get ready to start that. Hi, welcome. Lovely to see some comments coming in. Hopefully that's now sharing as well. So we're going to get started looking at log rules, logarithms, and it'd be lovely to hear from you if this is something you've done before and this is just revision, or if this is brand new and you've never met it before. It'd be great to hear. So this is log rules from the start, a really important pure maths topic, and we're going to look at it from kind of what we should already know and build it up. So log rules, we'll get started. Welcome. Do say hi if you've just joined. It'd be lovely to hear from you. It'd be lovely to hear answers to questions in, like, see them in the chat as well. But if you want me to re-explain anything, please do feel free to ask as we go. Welcome. Hi, everyone. Oh, lovely. Got some comments coming through. I can see those now. Welcome. I hope you're all keeping well. We're just about to start log rules. I'm Max. I'm head of maths at Snap Revise, and I've been teaching A-level and GCSE maths for the last sort of 4 or 5 years now, at a really interesting time to see how A-levels and GCSEs have changed in terms of the syllabus and also kind of how exams are structured and everything. So it's really important that we kind of pinpoint exactly what it is that we need to know that are maybe the changes in the A-level. And log rules is one of those key topics that has been on the A-level for years, but we need to know really kind of carefully. And so we're going to be looking at that today. We've got this promotion going on, 25% off courses, back to school offer. So there's the code. I'll talk a little bit more about that at the end, but feel free to kind of make a note and I'll show you how to use that. So if you enjoy the web class and you want to use that for the kind of courses that we offer, that's the code and I'll talk about it at the end. I'm keen to get cracking with the log rules stuff now. Welcome to all those that have just said hello. I hope you're all doing well. Please let me know if logarithms is something you've done before or if it's brand new. It'd be really good to give me an idea of if this is revision or not. What we're going to look at in this session is defining what the logarithmic function is. What is a log? What is a logarithm? Look at simple logarithms and values, and then look at some of the rules for finding sums and products of logarithms. So I'm not going to go into exponentials too deeply and logarithmic graphs. I'm really just going to introduce and sort of set the scene of what logs are and looking at the log rules. So to start with, we're going to think about what we already know and define these kind of key ideas. So just as a kind of real basics of what we should hopefully be happy with. Oh, lovely. No worries, brilliant. Thanks for letting me know. So some people, this is hopefully going to be useful revision of a topic that obviously grows into year 13 content as well. So it's useful for all those studying A-level maths. So thanks, that's great. So here we go, x to the 0, anything to the 0. Hopefully we're happy with index laws, but that is always going to be 1. Lovely. Oh, brilliant. Right, cool. Thanks, guys. I'll keep an eye on the chat, but that's good. Thank you for letting me know. So x to the 1 is x. Anything to the power of 1 is itself. X to the a times x to the b. Let's be careful here. We add them, don't we? So just going index laws, we need to just be absolutely confident with before we can get into logarithms. X to the a divided by x to the b would be x to the a minus b. And then these two here, we need to be careful. Negative powers, we know is 1 over their reciprocals. So that would be 1 over x to the a. And when we've got a power to a power, we times the powers. So we get x to the ab, the product of them. Welcome if you've just joined, guys. Do feel free to say hello. And also let me know any answers or questions as we go. Now, inverse functions, just as a bit of a side note, is something we've hopefully met over the course of GCSEs and A-levels. They're just kind of functions that undo the original functions. So if I add a and b to get c, I know that if I add a and b, but then I minus a off, that would just leave b. So the inverse of addition is subtraction, and so on. So we can kind of basic rearrangements for like linear functions is fine. Obviously for multiplication, then we'd have division would be the inverse. And for things like sine or trig functions, we know that the inverse of sine is arc sine, which we know on the calculator is like the shift sign, and it's denoted with the inverse symbol. And that would undo the function and just spit out a. Okay, so what we're going to do today is we're going to look at logarithms from scratch, which, as I said, is initially covered in pure maths in year 12 generally, but grows and grows and becomes a really important part of the pure maths content. And this is on across all A-level exam boards. Logarithms are really crucial that we understand them and know how they work and operate. So the logarithmic function, we're going to sort of set the scene and define this to start with, and explain what it is. So the logarithmic function is the inverse, which is why we kind of just introduced what an inverse function is the inverse of something called the exponential function, which you may have come across before as well. Exponential function. So a to the power of b is c. That's something we can kind of get on board with. If we have numbers, we can kind of go, okay, that's fine. That to the power of that gives me that. The way we undo this is we use something called a logarithm. So what this is effectively the definition. Log base of a of c is equal to b. So log base of this, of the answer, gives me the power that gets you that answer. So this takes a little minute to work through, especially as this is quite new for a lot of people. So if we've got a to the power of b is c, then log base a of c gives me b, the number that was in the power. So this is how and we'll look at the kind of questions that this will solve, and it's really kind of useful. So that is the definition of what the log function does. It kind of undoes those exponential scenarios where we don't know what the power is. It allows us to find the power that gives that answer. So I'm going to go through some scenarios here. Now, this can all be done on the calculator, but the examples we've got here are doable without. So if I said log base 2 of 32, I'm effectively saying 2 to the power of what is 32. So if we think about powers of 2, this is a nice one. Can anyone suggest what the answer to this will be? Log base 2 of 32. So 2 to the something is 32. What's the something? Brilliant. Thanks for the answers there, guys. That's lovely. The answer to this would be 5, because this to the this equals this. I don't know if that's a technical way of doing it, but that's how I think of it. Excellent. Thanks, guys. So the next one, log base 9 of 3. Now let's be careful here. 9 to the power of what is 3? So we've got to be careful like which way around we do this. So this to the power of something gives me this. So it's 9. So that's what this is solving. 9 to the what equals 3. And the power will be 1. We've got to be 1/2. If it was 3 to the power, then it would be squared. But we've got to be really careful with that. Excellent. Right. Thanks, guys. Lovely. Now, the next one, let's do this one down here. Log base 5 of 125. That is effectively answering the question, 5 to the power of what gives me 125. And again, that's a nice integer value that comes out as 3. No worries. Don't worry. But we have got to be careful with this as well. But don't worry if any answers are wrong or anything, because it's, we've got to be, we're doing it all non-calculator as well. So that's great. This one here, 2 to the power of what? Let's be careful with this, is 1/64. So we've got to say 2 to a power that's given me this sort of reciprocal setup. So we might think, well, 2 to the power of what is 64? So how am I going to get that over 64? So 2 to the power of what is 1/64? Well, that would actually be, so 2 to the power of what is 64? That would be 6. So if I want it to be 1/64, that's going to be 2 to the power of -6. Okay, so -6, if it was a root, that's when we would have a fraction. Excellent. Right, thanks, guys. So we've got to be careful with these, but it's worth going through. And thank you so much for all the engagement in the chat. That's brilliant. So this next one here, log base A of 1. Now, we don't even know necessarily what A is. Could anyone suggest what something to the power of something is 1? Welcome. Hi, guys. Lovely to see the comments, and thank you for joining. Hopefully this is useful for everyone. Welcome, Marion. Hiya. Yeah, excellent, guys. Well spotted. 0. Log base A of A. A to the what is A? What power gives you the thing itself? So this one will be 1. Brilliant. Right. Now, going back up here, this kind of ties in with the definition of a logarithm. Log base A of A to the x. Well, remember that it's an inverse. So by definition, it undoes what the actual function is here. So log base A of A to the x. So A to what power gives me A to the x? A to the something equals A to the x. Well, the something has to be x. And this is the definition of inverse functions. Doing log base A of A to the x undoes it and spits out x, just like how arc sine or inverse sine of sine spits out the angle. So in a similar way, A to the power of log base A of x would also be x, because it's an inverse function by definition. So hopefully that's kind of clear. But I think that definition is really important. And what we're going to do now is see how we can use this to solve logarithms, problems involving logs. So here we go. This one here. Now, if I want to solve this problem, 2 to the power of something equals 16, I'm going to take log base 2 of both sides. And you might have spotted a different way to do this question, which is fine for this one, but it's not always easy to do it if it's not nice numbers. So if I do log base 2 of 2 to the 3x plus 1, the log base 2 of 2 basically brings down the 3x plus 1. Basically, do you see what I did there? Basically brings it down. So 3x plus 1 is equal to log base 2 of 16. Now, log base 2 of 16 is just a number you can work out. Log base 2 of 16, 2 to the power of what is 16? 2 to the power of 4. So 3x plus 1 equals 4. It's become basically a really sort of, I keep saying basically now, linear equation. 3x plus 1 is 4. 3x equals 3. X equals 1. And if we check it, 2 to the 3 times 1 plus 1, 2 to the 4 equals 16. It works. So that's how we've used logarithms here. Now the next one, brilliant. Thanks for the answers, guys. That's superb. Now here, let's look at this one. What this is saying is if we rejig the information, this is actually saying 3 to the power of this is this. So I would interpret this as 3 to the power of 4 is equal to x squared. So that then tells me that 81, which is 3 to the 4, is equal to x squared. So that means that x is equal to plus or minus 9. Brilliant. Square root both sides. Well done. Good. Right, I'm going to keep going because we've got a fair bit to get through. So this next one here. So if you want to just give a little quick checkpoint, guys, just a 1, 2, or a 3 to let me know how you're feeling with that content. That would be great. Let me know. So let me know in the chat, just a 1, 2, or a 3, or a smiley face, or an emoji to let me know. Lovely. Right, let's keep going. So I'm going to just look at an exam style question of this. So again, reinterpreting this information, this basically means x to the power of this is this. So x squared is 64. So x is equal to 8. Why have I not written plus or minus 8 for this question? Because technically minus 8 squared is also 64. Why did I not write minus 8 as my answer for this one? Cool. And also looking at this here, just make sure we're reading the question carefully. There are some little subtleties we've got to be aware of and be careful about. So next one, use logarithms. Lovely. Find the positive, oh, sorry, we've done that. Use logarithms to solve 5x minus 1 is 120. Give your answer to 3 significant figures. So 5 to the x minus 1 is 120. So what I'm going to do is I'm going to do log base 5 of both sides. Because 120 isn't a nice power of 5. It's going to be a decimal. That will bring that down as x minus 1. And make sure you are able to write this into your calculator as well. You know how to find the log button. So log base 5 of 120 plus 1. And if anyone could give that to me, brilliant, excellent suggestions there. That's superb. If you could give that to me to 3 significant figures, that would be superb. Check we've got the same thing. So I'm going to do x is then equal to log base 5 of 120, close brackets, plus 1. Superb. Let's check we agree. Looking at the answers coming in, I think I agree with that. So 3.97, and that would be it to 3SF. So well done if you found that answer. Lovely. Well done. So we're going to look at logarithmic laws now. So this is like how we do index laws. We're going to look at laws of logarithms. So if we said log base a of x, we're going to call that b, and log base a of y is c, then hopefully we're happy that x is a to the power of b by definition, and this is a to the power of c. Okay, so any number can technically now, because we've got logarithms, can technically be written as a power of any other number. So if I wanted to write 87 as a power of 10 to the x, I could just do log base 10 of 87, and that would give me the power to put 10, and it'll be between 1 and 2, because 10 squared is 100, so it'd be like 1 point something. So I'm at the stage where I can now effectively use logarithms to write a number as a power of another number. And that is really the purpose of being able to do this. So that we've set up 2 scenarios here where if I had x, y, that would effectively be a to the b times a to the c. Is everyone happy with that? So if x is a to the power of b and y is the same base to the power of something else, we can do logs of that to sort out what the powers are. But then x times y is a to the b times a to the c. Is everyone happy with that? You might think, where's he going with this? What's the point? We're going to derive a rule from it. But as I said, if you've got a product of 2 numbers and they can be written as the power of something with the same base, for example, 10 to the something times 10 to the something, then I can write it in this way. And from index laws, I know that that's the same as a to the power of b plus c. So what that's telling me is that log a of xy, if I take log base a of both sides, is just b plus c. So that tells me that the logs added up is equal to the product of the two things inside the log. So if I had log base something of 20, that's the same as log base the same something of 4 plus log base of 5, because those numbers times to make 20, it's the addition of their separate logarithms. So it might be a little bit confusing to go through, so do let me know if you want to clarify any step. But what we've done is we've effectively said that the log of a product is the sum of the individual logs of the two factors. That's what we've shown. So we've done it with a sort of very general example, but you can work it through with numbers. So that's one of the laws that we're going to be using. Do let me know if you've seen that before and if that is revision, because we're going to be doing that in some of the examples we go through. So that's one of the rules. And do ask me if you need anything clarified. But yes, so brilliant question. So where the laws of logs are coming from is kind of reverse engineering the index laws, because that's kind of what a logarithm is, as an inverse function of an exponential scenario. So excellent, thanks guys. So that's what we're doing. We're going, right, let's set up this general scenario, and we know what would happen with the indices, that if we times them, we add the powers. So the addition of logarithms actually refers to a multiplication. So that's what we're kind of looking at, and that's the rule we're putting in place then for how we deal with logarithms directly. We're using our knowledge of indices to say an addition really represents a multiplication. And so we've got this log rule now, that if we've got the same base and we're adding two logs, we're really timesing, because that's what the power would be doing. And I think that's the bit that maybe we don't have a lot of time to appreciate when we first learn logarithms. And it's a rule we really need to know from the start. So in a similar way for the division, you guys can probably guess what's going to happen here. That's like a to the b over a to the c. We know that that's a subtraction. So I know that log base a of a division represents a subtraction of the separate logarithms. Log base a of x effectively b minus c. So what we've got is log ax minus log ay is the same as log base a of x over y. So that's kind of the other log rule that we would have. Very good. And then a kind of final one we want to look at in terms of powers, which I'm going to do here, is if we have n log a of x, say that was 5 or 10 or whatever n was, that's like however many lots of that logarithm. So that's like this plus this. And are we happy that that's n times? So if it was 15, it's like the thing added to itself 15 times. So what that means is if we use the previous rule here that we've got, that we can kind of absorb that into one single log as log base a of x times x times x times x, blah, blah, blah. So effectively, log base a of x to the power of n. So the rule that we've kind of derived here, we have derived, shown here, is that the power inside the log can come down outside as a multiple. And this is kind of undoing the index law that a power to a power is a multiplication. So something to the n can come out the front of the log as a multiple, because it's telling you that's how many times it's been times by itself. So that kind of brings a few rules together there. So what we're going to do is we're going to kind of see this in practice now with some harder exponential and logarithm questions. So I'm going to move this on. Do ask me if any of this is new to you. I know that this is quite a lot to take in. These 3 rules are actually can be very confusing if you've never seen this before and you've only just been introduced to logarithms. but they are, as I said, the kind of reverse engineering process of index laws in a way that we can understand how the powers are behaving. So what I'm going to do is I'm going to move on and have a little look. So this question here, it's what we're going to do firstly. I'm going to talk us through how to do this. And this very much looks like an A-level question, doesn't it? It's like, okay, quite complicated looking when you first see it, but we want to be able to solve this. So what we're going to do to start with is we're going to use the laws that we've just kind of come up with, the log laws, to write in terms of a single logarithm. We don't want all these different logs floating about different places. So use laws to write in terms of a single log. And so what we got is you've got log 4 of x squared minus log 4 of x plus 2 equals 3. Can everyone see how I've absorbed that into there as a power using the power law we just described? And now I can actually go a step further than that. Because it's a subtraction and it's the same base, I can actually write it, the subtraction, as a division. So I've used both laws at once there. I've put the squared into the power, and because it's a minus, that really means divide. So I've got it all as one single log. So this minus this really means log of that squared divided by that. And I've combined it all into a single logarithm. So that's how we've used the log laws to tidy up the left-hand side. So then what I'm going to do is I'm going to take my understanding of the definition of a log to now get it out of the logarithm. So what I'm going to do here, this step, we're going to say is convert to an exponential. And the questions are going to get harder that we do now, guys, but hopefully this will be useful for you all. So this is where we convert it. So what we do is we know that this to the power of this is all the bit inside the logarithm. So x squared over x plus 2 is equal to 4 to the 3, i.e. 64. So then the final bit, well done if you've done it, is to solve algebraically. Great work. Let's have a look. So where we're at is going to boil down to a quadratic scenario, isn't it? So we're going to have x squared minus 64x minus 128 equals 0. You can use the quadratic formula or your calculator, however you normally go about doing this. And we're going to get the positive number of 65.9. Well done. Brilliant. So the reason that this answer has to be positive is because it has to be positive numbers that go into a logarithm. So that's something we'll kind of look at more carefully when we're looking at the functions and the graphs and stuff. But well done if you got that value. That's superb. We're going to do a few more harder examples like this. Yeah, logs, you can't take log of a negative number, because the power of a positive number will never turn negative because the asymptote is 0 of the graph and so on. So what I'm going to do, keep going, but really well done with that. So let's look at a few more examples. So this one here. So we've got 2 to the power of x plus 1 is equal to 5 times 3 to the 2x. Now, what's immediately more confusing about this is they're not even the same base. So what I'm going to suggest here is when we take logs of both sides, we have to take logs using the same base. So take logs of both sides. It's still the first step. Now you could use 2 or you could use 3, or you could just use something completely different. So I'm just going to use this notation just to get us a little bit used to it. I'm just going to write log. I'm just going to write log 2 to the x plus 1 equals log 5 times 3 to the 2x. Now, some of the older calculators had a button on them that just said log, and that conventionally meant log base 10. You can do log base anything as long as it's the same on both sides. So if you ever see on old mark schemes or you see it on older calculators, just log, it typically means log base 10, but that's a kind of good one to use because as long as you use the same thing, log can be anything. So even though the notation seems a bit sloppy to now not be writing a base, as long as it's the same base, it doesn't really matter. But when we see the word log written, they normally mean log base 10. So then what we're going to do is just carry on through this using log laws and doing the same process of trying to get it as a single logarithm. So use log laws to bring down x. No, I mean, it doesn't matter if you did mention the base, if you put log base 10, or even if you put log base 2. So you could do this a slightly different way using log base 2 and log base 3, or using log base 2 or log base 3, as long as it's the same one. And the question would maybe speed up in parts and slow down at different steps, but you'd get the same answer ultimately. The key thing is that you use the same log base on both sides. But yeah, you don't need to mention the base necessarily, as if you write log, it conventionally mean log base 10, but you still do the same process. So yeah, an ln, well done, natural log means log base e. So there's a few types of logarithms, but you can just write log for a question like this and work it through, and we'll see what happens. Really good. So what I'll do is I'll show you how this sort of ends up working out, and we'll try it with different bases. So if I bring down the x plus 2 as a power, then I've got log base whatever of 2 is equal to, now remember this multiplication can be split as an addition, log of 5 plus 2x log 3. Now, on the final step, again, we're going to solve algebraically. So I can expand the x log 2 plus the log 2 there and bring all the x's to one side and so on. So I'm going to get x log 2, whoops. This is good. These are really good questions to be going through. Minus 2x log 3 is equal to, and I'm going to bring the 1 log 2 across. So I've got log 5 minus log 2. I've kind of just want to clarify, because I've sort of jumped a step there. This one here does expand to x log 2 plus 1 log 2. And I've just rearranged it to get the following. So hopefully that makes sense to everyone how I've done that. I've got all the x's on one side, because what that will then allow me to do is factorize out the x and then do the division. So then x is equal to, and this is the cool bit where you can check it with different bases as well. So what we've got here is log base 5, sorry, log of 5 minus log of 2 over log of 2 minus 2 log 3. And what is really cool is that even if you used, so try it out on your calculator, use log base 10 and do log base 10 of 5 minus log base 10 of 2 over log base 10 of 2 minus 2 log base 10 of 3. Or use a different base, as long as it's the same, and it will still give you the same number. And instead of log, you could even use the ln button, as long as you use it everywhere, and it will still give you that same answer. Which is why, answering that question earlier, which was a brilliant question, you can afford to just write log, because the base, as long as it's the same, doesn't matter, because we're just manipulating how the indices would have behaved. So you'd ultimately get the same answer. But please do verify that you're happy with this and check it on the calculator. That would be really good. And then I'm going to move on to another example now, but we're pushing through some good, really like involved questions here. Check it and verify. Let me know in the chat if you've done it on your calculator and it's worked. That would be really good to know. Brilliant. Cool. Right, we're going to keep going. Excellent. Here we go. Next one. Right. Now this one, this is a little bit different again. What I'm going to suggest here is we're going to use a substitution. Can anyone suggest what kind of substitution we might use here? How could we make this look a little bit nicer? What could I let, let's call it u. What could I let that equal to? It's a sneaky hidden quadratic. Well done. So let's say let u equal to 5 to the power of x. Let's see what happens. Or y, we could use y. Brilliant. So what I'd get is, let's remember, this is probably the tricky bit. 5 to the x times 5 to the 1 is 5 to the x plus 1. Now, if that's u, then this would be 5 times u. Can we see that? That 5x to the 1 is the same as 5x times 5 to the 1. So that's u times 5. And then this one is 5 to the x to the 2. So that bit is u squared. So that's good. So hopefully this is really useful and we can see what to do here. Brilliant. Right, brilliant. So let's keep going and it makes it a lot easier. So what we've got is that this will become, this is pretty cool, u squared minus 5u plus 6 equals 0. So by using that substitution, I've turned this sneaky quadratic, this into a quadratic that I can deal with. Then I can solve that for u. So we'll do that now. No pun intended there. Solve it for you. You can solve it for me. Here we go. We're going to solve it for you. U minus 2, u minus 3. It factorizes nicely. And then u is equal to 2 or 3. Brilliant. So now what we can do is put it back into the context of the original equation and then solve using logs. So let's see what we get here. So substitute back the substitution that we had, and it's really quite quick. And take logs, so use logs. So we know that u is 2 or 3, and u represented 5 to the x. So 5 to the x is 2, or 5 to the x equals 3. Now again, if we think about it, 5 to the power of something is 2. It's like, well, that's a bit weird. Like 5 to the power of what is 2? That's fine. We can solve that using logarithms. So x is equal to log base 5 of 2, or, and they're the exact answers. You could do them to a few decimal places. That would be 0.431. 5 to the power of 0.431 is 2, or 0.683. Cool. Let me know if we've got that, if you want to check those as well. And there's your two answers. So you've solved that kind of hidden quadratic sneaky exponential problem using logarithms. I think that was a really good one to go through because it ties in with the earlier chapters of the pure maths, the quadratics, where you're using a substitution. So it's sort of bringing all those skills back again as well. And this is really how the course sort of evolves, and it starts to sort of cumulatively take on ideas you've seen in earlier chapters. Brilliant. Yeah. So let me know how you're feeling, guys. Let me know just 1, 2, or 3. And then we'll look at a nice couple of exam questions to really check we like this and we understand this. So I'm going to move this on. And just let me know in the chat there, 1, 2, or 3 on how you're feeling with that stuff. Lovely. Here we go. So thanks, guys. Thanks for all the answers and questions as we've gone in the chat as well. That's brilliant. I know this is quite involved and we've kind of gone through the topic very quickly if it's new to you, certainly. Let's look at this one because this isn't that bad. It isn't as bad as it looks. Thanks, guys. That's fine. Yeah, just to give me an indication of how you're feeling. As I said, we're going to do a few exam style questions now. I'm going to talk about the upcoming web classes and the kind of discount promotional code we've got going on for our courses at the moment. If you found this useful, but we're going to finish with a few exam questions that I would say just build up a little bit now in difficulty from this one, which is actually okay. So let's have a little look at this. Given that log base a of x is p and log base a of y is q, express the following in terms of p and q. Right, so let's look at this first one. Now we know from the log rule that that can be written as what? As an addition of the two separate logs. Brilliant. So we were told that log a of x is p, log a of y is q. Brilliant. So that's p, that's q. So there's your answer. That is p and q, p plus q. Excellent. Hopefully that's good. Let me know if that's okay. Well done if you got it. And let's look at the next one. Now this one here is log a. So it's quite a bit going on here. Now this is the same as log base a of a squared plus log base a of x cubed, because they're times together. Yeah, I'm just going to finish this one and then I'll talk about what we've covered so far, but we've done quite a lot already. We've gone from log rules from the start and we're just using them to work through exam style questions now. So what we're saying with this one is that a product in the logs becomes an addition and the division is effectively a subtraction. And another log rule we looked at is the power rule, whereby you'd bring the indices out the front. So that could come down here. So what we'd have is that this would be 2 log a of a plus 3 log base a of x minus log base a of y. Now, who can tell me in the chat? Well done if you've got an answer. Log base a of a, do we remember what this is? Log base a of a, log base something of itself is 1. So that just becomes 2 times 1 plus now 3 log a of x, we're calling that p. So 2 plus 3p, and log a of y, we're calling it q. So minus q. Yeah, really well done. So our answer to this one is going to be 2 plus 3p minus q. So I'm going to keep going. We'll do a few more logarithms-based questions now, and then I'll kind of recap and go through the snap revise stuff and the code and show you the website and stuff as well. Really well done if you got that. I'm going to keep going because these questions are good to sort of look over what we've covered. So the next one we're doing, use logarithms to solve this equation, give your answer to 3 significant figures, and then we're going to do the other question as well. So here we go. So these are good ones to go through. So what I'm going to do is I'm going to take logs of both sides. And again, remember with the notation, I can just use the word log. Don't have to write log base anything specific, because as long as it's the same thing, it'll work. Then I can bring the powers down. So I'd get 3w minus 1. Brilliant. And yeah, as I said, I can go over any bits at the end, but this is sort of the exam style practice now of it. And it's quite a full-on topic, but I think we've all done really well here today, especially those that this is brand new for, and others this might be revision. So this is where we're at here. Now I'm just trying to aim to make w the subject. So we're going to have 3w lots of log 5 minus 1 lot of log 5 is equal to 250 lots of log of 4. So to get w on its own, so I'd add that across and divide by 3 log 5. So I'd get w is 250 log 4. You guys can look this up on your calculators once you've rearranged it, plus log 5 all over 3 log 5. By adding that across and then dividing by 3 log 5 to leave w on its own. And if you've done that, very well done. I think the answer there I got, is it 71.4? Just check. Let me know if you got that as well. 3 log, I think. Let me just check. Log base, say 10 of 4 plus base 10, 5. If you guys want to check it on your own calculators, you can use any log base, as I said. So, oh, sorry, guys, that was my mistake. That is 72.1. Is that right? Yeah, apologies. I think I might have. Thanks, Lorena. Is that what you got as well? Yeah. So yeah, double check that. I think that's what I got there as well. Yeah, well done. Good. Right, just conventionally, we use base 10. You don't have to. You could use any base. You could have used 5 or 4 here. You would have ultimately got the same answer. I was just showing as well that shorthand, you could just use the word log. And traditionally on the older calculators, that meant log base 10. It's just like a nice one to use. But it wouldn't matter as long as you use the same base. But yeah, really good question. And then part B, express y in terms of x. So let's get it tidied up as a single logarithm. So that would be log base x of 5y plus 1 over, because it's a division 3, is equal to 4. Now, remember to sort of get it out of the log, you do that to the power of that is equal to everything in there. So what we know then is that x to the power of 4 is equal to 5y plus 1 over 3. So then I just make y the subject. So 3x to the 4, not to the 5, is equal 5y plus 1. So that tells me that y is equal to 3x to the 4 minus 1, over 5. Okay, cool. Right, we're going to keep going. And this one here, right, let's have a little look. This is one of those substitution ones. First of all, it says find the value which 5 to the power of something is 7. Can anyone do that for me? So part A should be really quick. 3 significant figures. 5 to the power of what is 7? Well, it's got to be bigger than 1 because 5 to the 1 is 5. And it's got to be less than 2 because 5 squared is 25. So it's going to be 1 point something. And you're going to use logarithms to do this. So that's really what logs are useful for as well. So we're going to do log base 5 of both sides, log base 5 of 7. And what do we get as our answer to this one? Let me know in the chat. Yeah, brilliant, guys. Well done. 1.21. So part B, we've got one of these sneaky quadratics again. And I'm going to let u, again, equal 5 to the x. So what I'd have is that would become u squared, because 5 to the x to the 2 is 5 to the 2x, so that's u squared, minus 12u plus 35 is 0. And then this does actually factorize to u minus 5, u minus 7, which tells me that u is equal to 5 or 7. So putting the substitution back in, 5 to the x equals 5, or 5 to the x equals 7. So if 5 to the x equals 5, x could be equal to 1. And if 5 to the x equals 7, well, look what we did. Here's one we did earlier. 5 to the x is 7. That was part A. Then x could be equal to 1.21. So there was a nice sort of leading into that question from the previous part. Right, we've done really well there. I think we've got one more question and then I'll take any questions you have and also show you a little bit about the courses that we're running. So that's really well done with these. We're going at quite a quick pace here. We've been quite ambitious with the content we've taken on. But here we go. Find the value of y such that log base 2 of y is minus 3. So just undoing the log there, we've got, that would basically mean that this to the this is this. So y is equal to 2 to the minus 3, which is the same as 1/8. So this is remembering that we've got to kind of keep track of our index laws and be really confident with those as well, because you're going to kind of use it all interchangeably, everything you've done. And as we've seen, we've had to do solving quadratics as well. So this one here, again, what I'm going to do here is I'm going to times up to that side, and I'm going to get log base 2 of x, now this, we've got to be careful, is all squared because I've times up. And that would equal to log base 2, 32 plus log base 2, 16. So that as a number is 5. That as a number is 4. So I've got log base 2 of x squared is 9. So log base 2 of x is plus or minus 3. So I'm going to work out 2 to the 3 and 2 to the minus 3. So x is equal to 8 or minus 1/8. Okay, so that was a bit of a different one there at the end. Hopefully the first bit we're happy with, that was just undoing a log. And then we times up and we kind of dealt with this one like an algebraic fraction, and then solved it. Remember that these bits are just numbers. You can just type those in, but you could have worked them out anyway. Log base 2 of 32, 2 to the what is 32, 5, and log base 2 of 16 is 4. So that whole side tidies up, that whole bit tidies up to 9, and then it's just a problem to solve from there. Really good. Yeah, very good. So 1, oh, hang on, not minus 1/8, well corrected. 1 positive 1/8. Thank you, Zainab, that's lovely. My intentional mistake there was spotted. 8, positive 8 or positive 1/8. Well done. That was great. Thanks for correcting. Yeah, absolutely right, guys. Well spotted. Sorry, I think the messages even came through a little bit later there, but thank you for correcting that. It looks like you guys spotted that immediately. So well done. Yeah, absolutely right. So some really good logarithms questions there to have gone through. So what we've looked at today is defining the logarithmic function, which was right at the start, the fact that it's like the inverse of an exponential. We've recognized simple logarithms, like ones that we could do without a calculator. We've looked at simplifying the sums and products of logs and the different rules that come about, the log laws. Any questions, please do let me know in the chat. But what I'm going to do now is just let you know we've got lots of web classes coming up. So do set a reminder on YouTube. The other thing I mentioned right at the start was that the Snap Revised courses, we've got a bit of a promotion on for the new year that you might want to use. If you've enjoyed the session today and are also interested in all the other resources we've got to help you with the brand new kind of A-level structure. Yes, pretty much, Zainab, that's what we were saying earlier. Good question. Yeah, absolutely. What I'm going to do now is just briefly talk about the courses, because there's quite a lot of resources tailored to the new A-level on the Snap Revise site, and then I'll give you that code again, just for those that are interested in that, because this will hopefully be really useful for those studying the A-level at the moment. So I'm just going to stop sharing this for a second, and I'm going to share the website, hopefully. So on the Snap Revise site, if you haven't been on it before, this is what we've got. So you can go on your courses, and if you sign up for, say, the maths course, and you look on there, there's so many different bits that are on here that are tailored to the new A-level. And I think this is such an important thing, because there's no shortage of maths resources on the internet. There's lots of brilliant websites with loads of past papers and so on. The problem with some of these papers is they're geared up for the old course, and bits have been taken off, bits have been added on, and everything on here has been really carefully designed to the new 27 or post 2017 structure for the A-level. So there's like diagnostic quizzes, all the revision notes are kind of beautifully presented, it's all really clear. The other bit we have is the web classes. So there's year 12 and 13 web classes scheduled every week, and drop-ins if you've got problems with homework or you've got tests coming up. We'll do any kind of questions you'd like us to look at, and you can send those in. And these are running really regularly, and that's sort of something you might be interested in as well. But aside from that, there's loads on the course. So you can kind of go through, do a kind of diagnostic quiz to see what you know. That was a good guess. I didn't even read the question there, but see how you get on. Oh, clearly guessing. Oh no, it doesn't work for long. So you go through, you do the diagnostic quiz, and it kind of works out in terms of the spec points, exactly what you know, what you need to know. And then we address that really carefully and tailor the kind of content to help you kind of gain what you need for each topic. And the whole course is broken down. So you've got the pure maths, you've got the mechanics and the stats, And every specification point, as I said, has been really seamlessly built in to every part of this course. So I think this is really what stands the Snap Revise content out from other online platforms, is that it's really geared up to the new A-level, bang on. So here, it will tell you what you know and what you don't know. And then what it will move on to is videos whereby you can jump to the bit you need. Questions can be sent in. And there's the exam pack. So you've got questions, again, targeted to the stuff that you need. So you can really delve into those key areas. Easy, medium, hard. The revision guides are really lovely. So they're kind of clear notes that are printable. The key points just laid out perfectly for every topic. And as I said, for the stats, for the mechanics, and for the pure, and it's all designed for the new A-level. So there's loads to explore on there. So the courses are the bits that you might want to sign up to sort of see what's offered other than just the web classes like you've seen today. I'm going to stop sharing that and take you back to the PowerPoint. Thank you again to everyone for working so well through that. It was lovely to take a really big topic on and get so far through it with you all today. I know for some people that was revision, and for others it was maybe brand new, and you can see that there's like a lot in there. What is really good, as I mentioned, with the web classes we run every week, is that you can have access to previous videos, go back and obviously see the topics in depth that you've been doing in school. We try and follow the general sort of scheme of work that schools are running, but some schools do pure and then mechanics and do it at a different pace. Everything's on there, and the backlog of videos and resources, so that you can kind of tailor your own revision to what you're covering at school. And as I said, the drop-ins will allow you to ask questions about exactly what you're covering at the moment. So it's really a kind of big package, a big course that will hopefully be really helpful in tailoring the support and help to what you need, because it's a big A-level to take on. Maths always has been. It's one of those subjects that, you know, it's so much breadth to it, and there's a lot of new content on top of the GCSE that has been tweaked over the last couple of years as well, and that's what we've been really carefully focused on, and you can see from the resources on the site. So do check it out. There is the code, as you can see in the chat as well, the New Year 2022 code. So if you're interested in doing the regular web classes and the courses and looking at kind of the extra resources that are on there, please do check that out. It'd be lovely to see you in some of the weekly sessions as well. And as I said, we've got the YouTube ones coming up again, so just keep an eye out for all of that. But thank you again so much for spending that time on Sunday to work through a big, full-on pure maths A-level topic, and really well done. I'm going to stop sharing that there and say thank you again. Well done. Have a good rest of the weekend. Keep well, and hopefully see you at a session soon. Well done, guys. Thanks again. And yeah, brilliant answers and questions through the chat there. So really well done. Have a good week and keep well, as I said. Cool. Thanks, guys.